This is a continuation of the last lecture for algorithms and data structures since we ran out of time. One thing we didn't talk about is when can we use dynamic programming, and well, we mentioned it a bit in class, but it's essentially for sequential decision making where you can make an optimal decision by just looking at the solution to a subproblem and just figuring out one more step. So here we're adding one letter at a time in our diffing example. In the seam carving, we're adding one more pixel at a time. And if we have the optimal seam up to a pixel and then we add one more pixel, we can continue to have the optimal seam. Could we use dynamic programming for the TA assignment problem from last lecture? Well, the answer there is no, because it doesn't have this structure. So you could assign TAs to, say, 3 courses, and then when you try to look at a 4th course, as we saw in class, you may realize, oh, we have to reshuffle all the work we did for the first 3, even if what we had was optimal just for the first 3. So they're somehow more entangled with each other, and so we can't just look at a subproblem and take the optimal solution for the subproblem and have that end up being optimal in the whole thing. So let's go back to the diffing example. We had this hello example that we were using in class. We had this table, and I want to go through even more how we get these entries in the table. So let's start with this entry 3, 1, which means aligning the first 3 characters of x with the first 1 character of y. So aligning x, x, h with h. There's 2 cases that can happen when you're aligning. Either the last letters match or they don't. In this case, the last characters match. We have a h here and h here. And so what we can say is that the optimal alignment here is going to be the same as if we just deleted those 2 h's. Because if we had the optimal alignment of xx with nothing, which is this element right here, then we don't have to pay any extra cost to add an h at the end of both strings because they just match. So the score is the same. We don't need to highlight either of them. So that's how we jump from this 2 to this 2, and you'll see that in the code with the if statement. So opt3, 1 is 2, and opt2, 0 is 2. These are those 2's that we just talked about. So here's the more complicated case when the last letter don't match each other. So let's consider opt5, 2, 0, 1, 2, 3, 4, 5, 0, 1, 2. So that's this element right here. How did we get this 3? Well, we need to solve the subproblem, the first 5 characters of x, which looks like this, and the first 2 characters of y, which looks like this. And they don't match. So we already know right away that we can't just do what we did up here. We also happen to know in our heads that these are kind of the right alignment, that the HE is going to match with the HE, but the algorithm needs to figure this out. That's the algorithm that we're implementing. So here's the key point that I think I was missing in lecture. When we're trying to match this string here to this string here, because the L and the E's at the end don't match, one of them has to be highlighted. There's really only 2 choices. We're going to highlight the L, or we're going to highlight the E. That is, we're going to say the L was a deletion or the E was an insertion. And basically, we're just going to explore those 2 options. The L is highlighted and the E is highlighted, and we're going to see which one is better. And what was tripping me up, and maybe you as well, is that actually in the real output of the alignment of the entire strings, we happen to know neither of those things are highlighted. The hello is going to appear in both, and so none of those things are going to get highlighted. We're just going to have hello, hello. But that doesn't matter, because right now we're only focusing on this subproblem, XX, HEL, and HE, and we have to forget about the bigger picture and just think about the subproblem. And in the subproblem, because the last letters don't match, it is true that one of them has to be highlighted. And those are the 2 decisions, the options we have to consider and make a decision between which one would be a better approach. And at the end, when we're done, if I scroll back up here, we talked about kind of roaming our way back from the end to the beginning, and that's how we're going to figure out the optimal highlighting. What it basically amounts to is we're not going to pass through this phase of things. We're not going to use a subproblem where the L is highlighted, nor are we going to use a subproblem where the E is highlighted. But as I said, we can't know that yet. We have to fill in the table one entry at a time. So for now, solving this subproblem, the 5-2, we just need to focus on making the decision. Do we highlight the L or do we highlight the E? And so in order to do that, we think, well, what does it mean if we highlight the L? If we highlight the L, it means that L was a deletion. And so what that means is that the stuff without the L needs to get aligned to the output string. So XHE needs to be aligned with HE. And so that says, oh, I did it the other way around. Let me do it like this. Okay. So the stuff without the L needs to be aligned to the stuff without the E. And we've already solved this because we've already solved all the smaller subproblems. So in the case where the L is a deletion, then we're saying, well, this would have been the subproblem. And this subproblem we already did. We can just look at that element above it in the op table and say the score is already 2. And so now when we add that highlighted L, we're paying an extra penalty. So we would go from a score of 2 to a score of 3. Then we need to consider the other option where the E is highlighted. So that E is considered an insertion. And that looks like this. In the case where the E is highlighted, we're basically considering the E to be an insertion. And so we can match the H's, and all the rest of the stuff is considered deletion. And so we know kind of intuitively that doesn't make sense because we deleted an E over here and then we inserted an E back over there, and it's better to match them. And that is what the algorithm is going to figure out. But in the code, we're actually trying both options. So again, this 5-1 is a subproblem, and here it says there's 4 highlighted. We can see them 1, 2, 3, 4. So we have 2 options. We can either highlight the L, say the L is our deletion, and here's where that comes from. We have highlighted these, and then we've added the L and highlighted it. And this subproblem had a score of 2, and so then we can add 1 to that and get a score of 3. Or we can say, oh, we're highlighting the E, so this is what we had before we added the E. And this has a score of 4, and again, we know that because it's a subproblem, and then we add an E and we would get a score of 5, and which one's better? And so we take the minimum, which is going to be 2 plus 1, that's better than 4 plus 1, and that's where we get that 3. So when we actually look at opt of 5-2, here's that 3. It's a 2 plus 1. So that's the idea of how you decide whether to look at the element above or the element to the left when the 2 characters don't match. Hopefully that was somewhat helpful. I also want to go through the vectorization stuff more slowly. So we had time for some of this. We created 2 arrays with 10 million elements in each. We timed how long it takes to add. So x is full of zeros. We're going to add 1 to each element so that y is going to be full of 1. So we timed how long that takes with a for loop. We timed how long that takes like this. It's very, very much different. And so the question is, why is it so much faster? I don't think 200 times looks right to me. I think it's more like 40 times, maybe. But anyways, this ran a lot faster. So we did talk about this to some extent, but now we really want to get into the meat of it more with this broadcasting solution. So up there we were just looking at adding 1, and now we're looking at finding the distance between 2 vectors. So we have this vector with 100 elements in it, this vector with 100 elements in it, and this is the formula for Euclidean distance. And I can rerun these cells. I'll get different answers because they're random. But here is the distance between 2 vectors. So I'm just subtracting x1 minus y1, x2 minus y2, etc., squaring them, and then summing them all up. And then where the problem got more complicated is if you have a whole bunch of x vectors and a whole bunch of y vectors. So maybe every movie can be represented as a vector with like 100 properties about the movie, and you have a whole bunch of these Netflix movies and a whole bunch of these Amazon movies, and you want to find similarities. What's on Netflix that's similar to what's on Amazon. So you want to find all these distances and maybe look at the small distances or something like that. Okay, so here I've created nx is just the number of x vectors, 5, ny is the number of y vectors, that's 3. And so if I have 5 vectors, I'm just storing that in a two-dimensional array. So now each of the 5 rows of capital X is one of my vectors, and each of the 3 rows of capital Y is one of my y vectors. And so I need to compute 15 distances. Okay, so I initialize an array where the distances are going to be stored. It's a 3 by 5 array, sorry, 5 by 3. Then I have my loops. And I'm simply calling this code we had before, except I replaced x with the ith row of capital X, and I replaced little y with the jth row of capital Y, because remember, I'm storing those vectors as rows of these 2D arrays. And then I'm just sticking the results in squared distances, and I can run it, and I get some results. And then all that was happening down here is I just copy and pasted this code here, but I put it in a function so that it'd be easier. I could just call the function. That's the only thing that's happening here. So I make some random x's and y's, I pass them into the function and get some output. The output will be different every time because these are just random arrays. Okay, so when it got interesting was when I actually made huge numbers of arrays. So I have 1,000 vectors, each of length 100, another 1,000 vectors, each of length 100. I want to find the pairwise distances, so I have 1,000,000 distances to compute. x1, y1, x1, y2, da 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 da, all the way up to x2, x3, and so on and so on. So, well, I already ran this in class, but we can run it again, and I guess it takes about 10 seconds. And the question is, can we make something even faster than that? So note that this is already, in a sense, vectorized. np.sum is summing 100 things without a loop. So that's actually much better than if you used a loop for this sum, which is I have below. It's even slower. But we still have these two loops, which it turns out can be avoided with broadcasting, which is maybe a little surprising. And so here's the one-line version of this function. And we can't really make sense of it unless we pick it apart a little more. So here's the shape of x. And here's the shape of y, and Tom talked about making these things compatible. So the hundreds are compatible, but the 5 and 3 are not. And so what we're going to do is we're going to create extra dimensions. Tom called this np.newAxis. It's the same if you do that or none. It makes no difference. So if I add a new axis to x after this 5 dimension, then the shape of x is 5 by 1 by 100. There's still 500 numbers in it, just like before. I just changed the shape in this weird way. And same with y. So what I've done here is I've changed the shape of x from 5 to 100 to 5 by 1 by 100, and y from 3 by 100 to 1 by 3 by 100. And now these are compatible if you think about broadcasting, because we go from the back, 100 and 100 is compatible, anything in 1 is compatible, so that's fine, and anything in 5 is compatible, and that's fine. And now when I subtract x minus y, it's actually filling in these extra dimensions. So you could basically think about it as it's making a copy of x for each y, and it's making a copy of y for each x, and that's how I end up getting all pairs of x and y. So I end up with something that's going to be 5 by 3 by 100, and I can show that to you as well. Again, the none and the new axis are interchangeable here. It's just stylistic. So take a look at this. Now it's 5 by 3 by 100. So what an ijkth element of this is saying, well, I can even show you. Element, I don't know, 1, 2, 3 of that. It's saying take element 1, 3 of x minus element 2, 3 of y. So the way we do this, we end up actually getting all pairs. because again, the shape is 5, 3 by 100. So the first index is which x vector were you looking at? The second index is which y vector were you looking at? And then we're subtracting. And so we still get the 100 dimensions because the x vectors and the y vectors both had length 100. Now we square them. That just squares every element in our three-dimensional array. And then we call np.sum axis equals 2. Axis equals 2 being this axis because we're indexing from 0. And so I'm summing over this, what I want, which is along the length of the vectors. And I'm just getting something left that is size 5 by 3. So here was my original version. Here's my broadcast version. And again, this is returning something 5 by 3 because I'm making these weird shape things. 5 by 1 by 100, 1 by 3 by 100, broadcasting them to 5 by 3 by 100, and then summing away this last dimension to get something 5 by 3. Except it's super fast. Oh, these are the big ones. So this is pretty convenient. I mean, you might argue this code is less readable. I guess I'd probably agree. Yeah, probably. But still, it can be quite a bit faster. So this I skipped over in class as well. This is the worst implementation where you keep these two loops, but you don't even use np.sum. You actually use yet another loop to do the summing. And so this thing is, well, yeah, I won't run it if it's going to take too many minutes to run. But basically, if there's a clever way of getting rid of loops, then it's usually good. So now, since I'm not taking up lecture time, I could just briefly talk about the optional thing. So scikit-learn is a package you'll use in 571. And it actually has a function that computes these Euclidean distances. Squared equals true just means give me the squared distances, like don't square root them. So they have a function that does that, gives me the same results. And when I time this, it's extremely fast compared to, so these are the big arrays that I'm timing. So instead of, I was proud of my improvement from, let me scroll up and see, 3 seconds. I was proud of my improvement from 8 seconds to 3 seconds, but this package is actually doing it in 30 milliseconds, which is totally nuts. So that's about 100 times faster than our implementation. And here there's actually a trick that is really a mathematical trick rather than broadcasting or a Python trick, which is that we're computing x minus y squared type things. But you could actually expand x minus y squared out to x squared plus y squared minus 2xy. And that wouldn't seem that great normally because, hey, I have a subtraction and then a squaring, and here I have a squaring and a squaring and multiplication, multiplication. So it seems like more operations to do this. But when x and y are vectors, then what we actually end up with is something that we can write in terms of matrix multiplication. So this ends up, if you want to compute these for all the x's and y's, this actually ends up being the matrix multiplication of some big X matrix times some big Y matrix transpose. And matrix multiplication is the most optimized thing you could imagine in terms of even doubly optimized, both in terms of big O, we talked about fancy algorithms that are faster, and in terms of the implementation, matrix multiplication is just blazingly fast. So that's how this scikit-learn thing actually gets an even faster pairwise distances, which is actually 100 times faster, which is very impressive. So we talked about these things in class. I showed the snake viz for maybe a minute. All I really want to say here is that, yeah, there's this famous quote, premature optimization is the root of all evil. Essentially, if your code is slow, make sure you know which part is slow. And if you have a part that's only taking 1% of the total time, you don't want to be spending all your effort improving that line of code when the thing taking 99% of the time is really what matters. So you can play around with this, read the documentation, but profiling is basically just a way that will tell you what part of my code is slow, and it'll say this function f is slow, and then inside of f, here are the particular lines of code that are slow, and then in those functions call those functions, and it's really cool. So I'll just leave that for now and move on to this. Other ways of speeding up Python code. So there's numba. Numba is it's called a just-in-time compiler. Basically what it does is, we saw this at the very beginning, this being slow. What numba does is it basically says, oh, I'm just going to look at the next few lines of code and realize, hey, this actually looks like a loop where you're just adding one to a bunch of things over and over again. So I'm going to take that into account and make the whole thing fast rather than just taking things one step at a time. So all you have to do is you have to install numba, and really you just put this decorator. Again, we didn't really talk about decorators, but it's just this thing you put above your function definition that starts with an @ and it essentially modifies the function in some way. So all you have to do is add this, and it makes it a lot faster. So, well, I should probably remember how fast it was without doing that. So half a second versus, well, we can already tell this is, okay, 10 times faster. So that's pretty awesome for typing 5 characters into your Python. Oh, here it says, recall that it took about 7 seconds last time. Okay, so that's pretty cool. And it's a useful tool, and yeah, why doesn't Python always do this? Well, I think it goes back to the fact that Python was not designed as a numerical computation programming language. It's a general purpose programming language that just happened to become super popular for numerical computation, data science, machine learning, etc. So the default Python stuff is sometimes not exactly what you want, and this is really easy to deploy way that may speed up your code. So check that out. And there's just a couple of other options. So Cython allows you to kind of interface Python with C. I haven't used it myself, but it's another way of speeding things up. And then PyPy is just a completely different implementation of Python. So it's Python itself is a program. When you execute Python code, you're basically running a program called Python and giving it your program as an input. And so someone essentially just rewrote Python, the program, to make it execute other programs faster. And the problem with it is it's not compatible with all libraries, and it's pretty non-standard. But again, premature optimization is the root of all evil. So don't use this unless you really need to, but it's something to be aware of if you're in a case where your code is too slow. Also, just a note, because I got confused myself about this, there's PyPy with a Y and PyPy with a capital I that have not, they're completely different. So don't get those confused. This is a different implementation of Python, and this is the Python package index, which is kind of like CRAN for R. If you haven't seen that yet, you'll definitely be seeing it in workflows or collaborative software development. Okay, the next thing is parallelization. So if you've heard of Moore's law, it stated that computing power would double approximately every 2 years, which actually happened for decades, which is totally insane, because we've talked in this course about how exponential growth is usually not. Exponential growth is pretty extreme, and so we had this pretty extreme growth for several decades. So now what's happened is that this isn't really holding anymore, but people are moving into parallel and distributed computing. So here we have this Fibonacci code from before. It runs in O of n. Here we have our adding 1 code from before. So this, again, loops through x and just adds 1 to each element of x. And this is also O of n. But the second one can actually be done in parallel. So the Fibonacci, each element depends on the previous element. So you have to wait to get that previous element before you can get the next one. But if you're just adding 1 to a bunch of stuff, you don't need to wait to add 1 to the third element before starting to add 1 to the fourth element, because they have nothing to do with each other. You can just do it all at the same time. So that's a case where the computation can actually be parallelized. So both O of n, but very different. One is kind of a parallelizable O of n, the other one is not. So I can actually count how many cores I have on my laptop. You can run this too. I have 4 cores, so hopefully I could actually use my 4 cores to maybe run this code 4 times as fast. We'll also talk about other parallel stuff in later courses. But just showing you the same number, library that I showed you before can actually do some of this. So here's 50 million zeros, and I'm just going to, let's see, each element of y is going to be an element of x plus a random number. So I've already got numba activated here. It takes 1.7 seconds. But now I'm activating numba and telling it to be parallel. And now it's going to take hopefully less than that. Okay, about half of that. So I guess that's pretty good. I mean, I think it was using my 4 cores. You'll never really get a 4x speed up with 4 cores because there's some overhead to doing parallel computation. But I'll take it. It runs twice as fast. That's still pretty good. Yeah, if it was the difference between 4 hours and 8 hours, you'd still be happy. So joblib can also do some memoization. Joblib can also be doing some parallelization. And I should also just mention parallel and distributed computing are not exactly the same. So what I just did was parallel computing on my machine. I just had a bunch of cores. But distributed computing actually means computation across machines. So I have 50 computers, and I want to use all of them to compute something together. And that we'll touch on in the web and cloud computing course. So yeah, of course I couldn't do justice to this topic in 5 minutes, but I hope it was a good introduction. So now we're back here, which we did talk about in class. So this is going to be the end of my lecture supplement.